line by line again. So now let's look at this one, similar to the previous one. So this is the quantity, and let's say, so that is your mixture. So you add 200 ml. At 200 ml, then you need to decide at what point are you. You know, is it at the equivalence point, before the end point, or after the end point, right? So all I say is you add 200 ml of that mixture. That is your titrant mixture into that. Then balance that, then okay, then calculate at what point you are, then calculate the potential. Then it turns out that it's beyond the end point, so you need to determine that, okay? So it is going to be beyond the end point. So at home, I want you to prove that it's beyond the end point. So now is calculate the potential based on the manganese Nernst equation. So it's written up like this, okay? And based on the manganese substance, don't forget the H+. It comes from that as well. So this is your half reaction. Your half reaction, okay? So it still carries the A. Okay, now the quantities. So the product here, the reduced product, on the permanganate. So I wrote that is equivalent to whatever the Fe2 plus is, right? So the total, because this is beyond the end point, all that quantity will carry to beyond the end point. So all that change into Fe3 plus. So all that change into Fe3 plus. So correspondingly, for manganese is 1 to 5. So it's only 1/5 of whatever the total is. So that is the total. Now it's Fe3 plus total. Okay, for manganese 2 plus is 1/5 of that. Okay, so this is 1/5 absolute quantity over the volume. The volume is important because now you have 2 volumes versus 1 volume, so you cannot ignore the volume. Okay, 300, 100 plus 200 is equal to 300. So anyone has difficulty to see this, to plug in. Okay, now this is going to be beyond the end point, so this is going to be excess quantity. So how much excess quantity is that? So, so the way to calculate is you calculate whatever the absolute that you have added first. Okay, this is the absolute quantity, right? MV, that's what you added practically. Then subtract the quantity reacted is how much is in a mixture, left in a mixture. So this represents the quantity reacted. So coefficiently, so reacted with Fe2 plus, right? So this is the total of Fe2 plus. Okay, then now 1 to 5 ratio. So we are talking about the permanganate here, how much is left for permanganate. So this is the reacted quantity for permanganate. Coefficiently equal to 1/5 of the Fe2 plus total, right? So the total divided by 5 is the reacted quantity of permanganate. Any problem with that? Everyone okay? Mr. Gaska? Are you okay? Cool. Okay, so volume is divided by 300. Now here, we did this calculation earlier, so this is added along with the titrant, 200 mils, so MV, single proton, so multiplied by 2. So this is total added. subtract the quantity reacted with Fe2 plus. Now is, we can see the 2 is equal to 10. So it's 10, so coefficient is 8 over 5. 8 over 5. More, that is less. Okay, so divided by 300 again. So continue with that, and you will get your answer for beyond the endpoint. Okay, so this just demonstrates the trickiness behind all these calculations. Okay, so now I would like you to do this, chapter 19, chapter 20, and chapter 21. Dr. Zalmer's website has very good, has an excellent examples in this type of calculation based on Excel. So he's retired. He's an analytical professor, retired, but he still maintains his website. So I'll go to his name, David Zalmer, and go Chem 102, and then go into.
Does he have a lot of examples of everything that we're doing?
Yeah, step by step.
And you're just now giving it to us?
I mean,
Look at it first.
I think his last name is Zimmer.
Huh?
It's Zimmer, I think.
No, his name. It's
Zimmer.
not the computer, it's Zimmer.
Yeah.
This is L, 2L. This is a person's name. Okay, so recall, you learn how to write cell representation. Learn that in 1B. So here's a reminder. So here is your actual cell diagram, for example, one electrode filled with the zinc ion solution with this concentration. Then you have a conductor that is zinc metal, okay, and then on the left is oxidation, and so this is anode. Then you have a salt bridge in between, and then on the right, then you have a copper ion solution with this concentration along with the conductor. Then your electron will go from left to right because you indicate this is oxidation, this is anode, this is cathode. So the electron is negative, so cathode will indicate as negative in this nomenclature because negative going to come in to make this negative, So physics is opposite. Physics call this plus, because you attract the electron. But chemistry call this minus because it's coming in with the electron. Okay, so reduction, red cat. That's how I remember red cat, reduction for cathode. Okay, cell representation. To draw that takes time. Then why not to use shorthand? So the slash means the boundary between two different phases. So liquid, solid, okay, to indicate one electrode with concentration on the left, so oxidation as well as anode. Then double slashes represents the salt bridge, and then there's a right electrode. So red cat is here, along with the concentration. Okay, if you were provided with one electrode, then you have platinum wire, you have the solutions. The solutions will contain these three chemicals with concentration. And then provide you with another electrode, also a platinum wire, a conductor, but will not participate in chemical reaction. Then here, HCl, and then you bubble chlorine gas into the solution, saturate with the chlorine gas. So use your imagination. If you combine the two into a complete cell, then you write a cell representation will be like this. Okay, then one, the platinum, then it is custom that to write the oxidized species first. Okay, indicate the concentration of gamma and other species, and then gamma, and then all the chemicals with concentration. Okay, then the salt bridge, make the connection. Okay, then on the right, the solution will be 1/, one is a solution, the HCl solution. Then on the right is non-solution on the right. So this is actually a gas. So gas is combined with solid metal. So that just one boundary rather than you have two boundaries. Okay, so keep that in mind. So the only tricky part is here that you need to combine the non-solution, non-liquid on the same side of the boundary.